Question 21. The diagram shows rectangles A and B. Rectangle A can be mapped to rectangle B by a single transformation. Javid says the only single transformation is a reflection in the y-axis because the rectangles are on opposite sides of the y-axis. Is he correct? And we need to tick to say whether yes or no and give a reason for our answer. Well, he's right that a reflection in the y-axis would map A onto B, but there are also other transformations that will do this as well. We could have had a rotation about this point here, which is 0, 2.5. If we rotate 180 degrees around there, A would map onto B. We could even have an enlargement of a scale factor of -1 about that point as well. But the simplest of the transformation that takes us from A to B is actually a translation that goes 1, 2, 3, 4, 5, 6 to the right. That will map that point onto that point, and therefore that shape A onto shape B. So I'm going to say no, he's not right. And an example I'm going to give, and I'm going to give this translation as an example. So translation of 6 to the right and 0 up. So translation of 6, 0 maps A to B. As simple as that. Okay. Part B, the diagram shows triangles CDE and PQR. CDE is mapped to PQR by combining two single transformations. So this time we're going to use two transformations. The first is a rotation of 90 degrees anti-clockwise about E, and we need to describe fully the second transformation. So I'm going to draw in this first transformation. It's a rotation of 90 degrees anti-clockwise about E. So about that point, we're going to rotate this shape 90 degrees anti-clockwise. So I'm just going to draw in what that is going to look like. Okay. We'll do it in blue. So point E is going to stay where it is. C, if that rotates 90 degrees anti-clockwise, I think it's going to end up over here. And D is going to end up over here. And that is going to be that shape rotated 90 degrees anti-clockwise. If you're unsure, you might want to use a piece of tracing paper to help you. Okay, and now I've got that in, just tidy that up a bit. Okay, now that I've got that in, I now need to find a second transformation that is going to map this onto this over here. So this looks like it's going to be, well, this is bigger, so it's definitely going to be an enlargement. And what I'm going to do is I'm going to try and find the center of enlargement. Now I can see it's kind of rotated as well, so that looks like it's going to be a negative enlargement. So in order to find the center of my enlargement, I'm going to draw some array lines. So let's do those in green. And point E would map onto point R, and that looks fairly obvious. Now it looks like this has been rotated, so I think that this point here is actually going to map onto point Q. And this point here is going to map onto point P. And we can now see that we've got a center of enlargement that's actually going to be over here. Okay, so our center of enlargement is actually at -1, 0. And we can see that this shape is twice as big, but because it's also been rotated, it's going to have an enlargement of scale factor -2. So we can say that it's an enlargement with center, and our center we said is at -1, 0, and a scale factor of, and we said that was going to be -2. So that's describing the transformation fully. I've said what the transformation is. It's an enlargement. I've said where the centre of enlargement is at -1, 0, and I've also stated the scale factor, which is -2. Question 22. PRT and QRS are similar triangles. So this big triangle and this little triangle are similar to one another. Which of these is equivalent to QR divided by PR? So we've got QR, which is that length there, divided by PR. So because the triangles are similar, QR divided by PR is going to be the same as any other length in the small triangle divided by its corresponding length in the big triangle. So QR divided by PR must be the same as QS divided by PT or RS divided by RT. So over here we've got RS divided by ST. That's not going to work. We've got QS divided by PT. That is going to work. So I think it's going to be that one. We'll just check the other ones though. PT divided by QS, that's the big triangle length divided by the small triangle length, so they are corresponding, but it's the wrong way around. And we've got RT divided by RS, and again that's the big triangle length divided by the small triangle length, so that's the wrong way around as well. So it's going to be QS divided by PT. Question 23. Here is a velocity time graph of a motorbike for 25 seconds. So 0 to 25 seconds at the time, and up here we've got the velocity. After how many seconds will the acceleration 0? So remember, the acceleration is the rate of change of the velocity. So what we're saying is, when was the velocity got to a point where it was not changing? So over here is where the velocity got to a point where it had a rate of change of 0 because it was changing in a positive direction, and then it went to change in a negative direction. So at this particular point here, its rate of change would have been 0. So if we read off that point there, that's going to be, well, if that's 5, that's 10, that must be 7.5 in between. And that's halfway between 5 and 7.5, so that's going to be 6.25 seconds. Okay, and anything between 6 and 6.5 seconds would have been acceptable there. Okay, part B says work out the distance travelled in the last 15 seconds. So in a velocity time graph, to work out the distance travelled, we need to find the area under the graph. So the last 15 seconds, so that would be from 10 to 25 seconds. So we need to work out the area under this curve over here. Now it is a curve, but it looks a little bit like a straight line over here. And in fact, if I was going to work out the area under that straight line, I could think of this as a trapezium, which is exactly what I'm going to do. So I'm going to draw in a trapezium over here. So it's going to look like this. And across there, and from there to there. So we can see that that's a pretty good approximation of the area under the curve there. So the area inside this trapezium should give us our answer. So if I have a look at the two parallel sides, well, this side has got a height of 20, 21, 22. Whoops, try that again. So this height's got a height of 22, and over here we've got a height of, and that looks like it's 15, 16, 17, 18. And then we've got the distance between the parallel sides, and that's going to be 15. So we know that to work out the area of a trapezium, it's going to be A plus B divided by 2 times by the height. So our area is going to be A plus B, the two parallel sides, so that's going to be 18 plus 22 divided by 2 times by the height. That's the distance between the parallel sides, which in this case is 15. So that tells me my area is going to be, well, that's going to be 40 divided by 2, which is 20 times 15. So that tells me that's going to be equal to 300, and it's the distance that's travelled, so it's going to be 300 meters. So my answer is going to be 300 meters, and that is 300 is the area of that trapezium, and therefore the area under that curve. Question 24a. We need to work out the square root of 12 1/4 as an improper fraction. So first of all, in order to find the square root of this, I'm going to convert this into an improper fraction. So 12 1/4 as an improper fraction is going to be, well, 12 is the same as 48 quarters, and we've got another quarter over here, so 12 1/4 must be the same as 49 quarters. So this square root of 12 1/4 is equal to 49 quarters. Now this is useful now because 49 is a square number and 4 is a square number, so the square root of 49 is 7 and the square root of 4 is 2, so that must be equal to 7 halves. Yeah, so I've just square rooted 49 quarters and got 7 halves. So my answer is going to be, as an improper fraction, 7 halves. Okay, part B says work out the cube root of 16 as a power of 2. So we want to write it as 2 to the power of something. So first of all, I'm going to rewrite the cube root of 16. So the cube root of 16 can be written as 16 to the power of a third. And I also know 16 is 2 to the power of something, isn't it? Because it's 2 to the power of 4. 2 times 2 is 4, times 2 is 8, times 2 is 16. So 16 can be written as 2 to the power of 4. So that means I've got 16 to the power of a third. So I can write that as 2 to the power of 4 to the power of a third. Okay, so using my laws of indices now, I should know that I can multiply 4 and a third together to write this as a single power. So that's going to be equal to 2 to the power of 4 times a third is 4 thirds. So the cube root of 16 as a power of 2, as 2 to the power of something, would be 2 to the power of 4 thirds. Okay, question 26. Expand and simplify x take away 4 times 2x plus 3y all squared. So in order to expand this, I'm going to start by doing the 2x plus 3y squared bit. So I'm going to say, well, 2x plus 3y squared. Well, I know that's going to be 2x plus 3y times 2x plus 3y. And that's going to be equal to, well, 2x times 2x is 4x squared. I've got 2x times 3y, which is plus 6xy. 3y times 2x, which is plus 6xy again. And then 3y times 3y, which is 9y squared. So that's going to be the same as 4x squared plus 12xy plus 9y squared. I now need to multiply this by x take away 4. So x take away 4 times 4x squared plus 12xy plus 9y squared is going to be equal to, and I'll do this down here, so x times 4x squared is going to be 4x cubed. X times 12xy is going to be plus 12 x squared y. X times 9y squared is going to be plus 9xy squared. Take away 4 times 4x squared, so that's going to be take away 16x squared. And then I've got this negative 4 times 12xy, which is going to be take 48xy. Negative 4 times 9y squared is going to be take 36y squared. Okay, let's see if there's any common terms here. So I've got an x cubed, an x squared y, an xy squared, an x squared term, an xy term, and a y squared term. So there's no common terms over here. So as this expansion, that there should be my answer. So I'm going to write it down on my answer line over here. I've got 4x cubed plus 12x squared y plus 9xy squared, take away 16x squared, take away 48xy, take away 36y squared. Question 25. In an office there are twice as many females as males. 1/4 of the females wear glasses, 3/8 of the males wear glasses, and 84 people in the office wear glasses in total. And we need to work out the number of people in the office. So it looks like we're going to use some algebra to solve this problem. So in an office there are twice as many females as males. So if we call the number of males x, so males, I'm going to call that x. So females, therefore, because there's twice as many, we're going to call 2x. Okay, so we've got 1/4 of the females wear glasses, and 3/8 of the males wear glasses, and 84 people in the office wear glasses altogether. So I know that 1/4 of 2x, so 1/4 of 2x, so 1/4 of the females wear glasses, plus the 3/8 of the males that wear glasses, so 3/8 of x, that must be the total number of people that wear glasses, so that must be equal to 84. Okay, so if I simplify this a little bit, I've got a 1/4 times 2x is going to be 1/2 of x, so 1/2 of x plus 3/8 of x is going to be equal to 84. Just thin the pen out a little bit. Okay, so if I multiply everything by 8, that will get rid of all of the fractions. So 1/2 times 8 is going to be 4x. 3/8 x times 8 is going to be 3x. And 84 times 8 is going to be 672. Okay, so that tells me 7x is equal to 672, and then x is going to be equal to 672 divided by 7. So let's just do that over here. We've got 672 divided by 7. That's going to be 0, 9, carry a 4, and 7 into 4, 742 is 6. So that's going to be x is equal to 96. So remember, we're working out the number of people in the office. So x represents the number of males in the office. So the number of females is going to be 2x. So the total must be all the males and the females added together, so it's going to be 3x. So we need to do the total equals 3x, so that's going to be equal to 3 times 96, and 3 times 96 is going to be 288. So our answer over here, the total number of people in the office is going to be 288.